ready. So
okay, so welcome back from this small break. And Anton is a PhD student in DESY also, I think, also working on Axions. And so I think you can start.
Okay, and thank you. So I put also the exercises in the chat, so you can have a look. Otherwise, so let me start. So the idea of this session will be to investigate a bit different couplings of axions, and the most basic ones are the coupling to gluons and the coupling to photons. So let me start from the coupling to gluons. So we have Lagrangian, which I wrote in the notes for the exercises. So here it contains the gluon field, the dual gluon fields which couple to axion. Here is the strong coupling constant squared and the axion decay constant. So now the first what we want to see is whether axion, so what symmetries does axion have, axion field has here. So and first let me show that the axion is shift symmetric at the classical level. So I think this is quite important for understanding the axion physics. So in order to do this, we can try to rewrite this term in terms of the total derivative term. So we will need some QCD here. So let me introduce the notation. So we will use, okay, so our notation for the vector potential will be that it is GS times the component times the TA, generator of the SH3 group, where TA is lambda A divided by half. Lambda are Gell-Mann matrices, and then so also the basic element is the covariant derivative, which is given by this expression, and also so then the field strength tensor can be rewritten as this expression. So containing the self-interaction parts of gluons, and then so we can check that d mu d nu, which is minus e d mu a nu minus e a mu d nu, so minus a mu a nu plus. So I just put this here and expand, and we see after some algebra, so plus a mu, that it is just minus I times d mu a nu minus d nu a mu minus I a mu a nu. So okay, so these are quite basic facts, but this is minus I times g mu nu, this field strength tensor. So the commutator of the covariant derivatives equals to the field strength tensor. Now we will also introduce components. So here this formula is written in terms of the components of the G tensor. So these components are defined accordingly to the A mu components as G mu nu equals G mu A TA. So G mu nu is also in the joint representation, and then so for these notations we have TA TB commutator equals I FABC TC, where FABC are structure constants of SU3. Okay, so now after this brief introduction, we can calculate the integral. so calculate the GG dual term. So here we will have that, we have G A mu nu. So we have the dual term is of course defined as 1/2 epsilon my mu nu lambda rho G lambda rho. So then we can rewrite G mu nu G G dual mu nu as epsilon mu nu lambda rho. So here we will also let us expand one of the tensors here in terms of the vector potentials. It will be d mu a nu a. So this one comes from here. I multiplied by so here what comes from the dual tensor, and also I absorbed. So here we had 1/2. And here I had d mu a nu minus d nu a mu. So multiplied by the antisymmetric tensor, it is just 2 d mu a nu. So actually 2 multiplied by 1/2, we get the factor of 1 here. And then we get also contributions from the self coupling. So we will have 1/2 now. Then G F ABC, so times A mu B A nu C. So here is just F ABC A mu B A nu C is commutator which enters the G tensor times GA lambda rho. So like this. Okay, now we want somehow to extract from here the derivative so that this term is a derivative of something. So what is the strategy which we can choose? In fact, okay, first let us expand this G lambda rho. So because as we will see G lambda rho here, it contains also the term like d mu a nu. So d lambda r a rho, and then the self-interaction term will actually cancel with this one. So why is it so? So let me expand. So this is d lambda a rho a. Yes, okay. So and we will have minus d rho a lambda a. And we will have also the self-interaction. So plus the commutator, and then this commutator will give us F, also F ABC times the fields, and it will contract with this F here and with these fields here. So in the end, because here this is like AA, the square in the so we have 2 fields here, 2 fields here. In the end, we will have 2 Fs and 4 A new potentials. So actually, this term will look like 1/2 G squared F ABC F ALM, and then as I promised, 4 vector potentials. Okay, so this is a term which arises from here, and we multiply when we multiply by this. So this term is actually 0, so which simplifies things. It is 0 because of the Jacobi identity, which tells us that in Lie algebra we have for the commutator this TA, TB, commutator with TC, plus all permutations of ABC equals 0. Okay. And so actually, if we consider, so the structure constants are themselves generators of the joint representation. So we will have here actually FABC FA. So this can be written as FABC FALM plus FABL FAMC plus FABM FALC equals 0. So actually what I did is just that if we choose the pairs from these 4 indices BC LM, and we sum over all the combinations, we get 0. So this is just Jacobi identity written in a joint representation. And then we can here we also see, so we have to here if we sum over all pairs, we get 0. But here, so actually it's multiplied by this BCLM, and we also have in the beginning epsilon mu nu lambda rho. So here, actually this expression is symmetric with respect to the interchange of pairs of indices, because we have epsilon mu nu lambda rho here, and it is symmetric when we move two indices, when we change like this and this indices, for example, in pairs. That's why, so this is symmetric when we do this pairing and symmetrization. And this is when we do this pairing and symmetrization, will give 0. So actually, that's why this term is equal to 0. So this simplifies our calculation, because now we don't have 4 fields multiplied by each other here. So we don't have a term. So, okay, let me then write what remains. We have GA mu G dual A mu equals, we will have epsilon mu nu lambda rho, then d mu A nu A G lambda rho A minus A nu A times d mu G lambda rho A. So actually this first 2 terms are just this term written in a bit different fashion. So then we can and we add what remains from here when we expand this. So we just put this here, and of course, because of the antisymmetry, we have 2 times d lambda A rho, and 2 times 1/2 equals 1. So in the end, we get G F A B C A mu B A nu C d lambda A rho. So as promised, A. Okay. So now, still it doesn't look like total derivative. So we have to do something else here. Okay, but first of all, we will look at this expression. So here, it is d mu G lambda rho A, and it actually can be, okay, so it is, it can be connected to the covariant derivative of G. So it will be useful. So we can write that it equals d mu G lambda rho A. And since covariant derivative also involves the action of A field here, so we have to compensate by minus G F A B C A mu A mu B times G C lambda rho. And so so here now, actually in front we have still the epsilon tensor. So when we contract epsilon tensor with this d nu G, or even with the covariant derivative G, we actually get the expression epsilon mu nu lambda rho d mu G lambda rho A, and this equals to 0, again. So why it is equal to 0? Because it is just the Bianchi identity, which again follows from the Jacobi identity as usual. So here we have, so why is it so? Just because as we showed, G is so G is a commutator of covariant derivatives actually. Here we have covariant derivative acting on G. G is in the adjoint, so actually this is just epsilon mu nu lambda rho d mu d lambda d rho. So here I just rewrote this in terms of solely the covariant derivatives. And here we have, so we have partial derivatives. Remind you that we have partial derivatives minus E A mu A T A G here. So this is definition for the covariant derivative. So the partial derivatives commute, and then the TAs, they do not commute, but in this expression, they in the end sum up to 0, because this is just the Jacobi identity. We have to just sum all these commutators TA, TB, TC, and again anti-symmetrize because of the epsilon tensor, and so in the end we will get 0. That's a short reminder why the Bianchi identity is this. So in the end, so this term just disappears from our calculation. We are left with this term. So yeah, and this term. So this term is already the total derivative. So this is good. Okay, so this term we rewrote in terms of this. So in the end, what we have is G A mu G dual A mu equals, so it will be epsilon mu lambda rho d mu A nu A G, G lambda rho A, total derivative already, and then plus G F A B C A mu B times, so here 2 A nu A d lambda A rho A plus A nu C d lambda A rho A. Okay, so why this? So this term we already had, FABC, AB, AC, d lambda AA, as you remember from here, yes. But then we also had this term here. So again, the term with 4 A's vanishes, just as before, but here we have also d lambda A rho. So and we will have a factor of 2 here because this is antisymmetric. So again, multiplied by the epsilon tensor. So we'll have factor of 2 here, and this d lambda rho coming from this g lambda rho. So so in the end, actually, we have this expression, and this already looks much more like a total derivative, just because here notice that the two terms here are both just 3, so product of 3 A fields, and then we have one derivative. So actually, because it is product of 3 A fields with different indices, but all the indices are anyway anti-symmetrized because of mu nu lambda rho. That's why actually all these A are on the equal footing basically, and we can. That's why we can just apply this d lambda derivative to any of them, and it will be absolutely the same. So that means we can just put the derivative outside of all the expression, and that's all. So of course multiplying by a factor of 1/3 in the end, because here we have 3 components, 2 here, 1 here, but in the end of course if we put derivative outside, then we will have just 1. So so what we get in the end is epsilon mu nu lambda rho then d mu a nu a g lambda rho a, and here minus 1/3 is promised gf abc, and d lambda times just 3 components of the vector potential, and that's all. So actually now, okay, very good. We have finally the derivative here. So what we see in the end is that GG dual term, which I wrote, is actually a total derivative of some vector k, which is given by k mu equals, so it is given by the following expression. Okay, let me write with the right normalization already. 1/2 gs squared epsilon mu nu lambda rho g lambda nu a rho a minus 1/3 g s f a b c a nu a lambda b a rho c. So finally, and this can be also rewritten, of course, in terms of the fields themselves, not the components. So this will be epsilon mu nu lambda rho trace of g lambda nu a rho plus 2I divided by 3 a nu a lambda a rho. So here, of course, in writing this FABC in terms of the fields, so what we used is that actually trace TA, TB, TC, so where TA, TB are in the commutator, equals to so I divided by half a FABC. So that's why we can rewrite FABC in terms of this trace, and then we can rewrite everything in terms of fields, and we get here this extra 2. So we get 2/3. Okay, very nice. And yeah, so the first question is solved. So actually, so in the end, what we showed is that axion couples like GG dual, but actually it is it can be written A d mu k mu. Now, yeah, and from here we see that if we integrate by parts now, that it will give us d mu a times k mu, and so now the A enters as a derivative. It is so the axion field is shift symmetric. However, this is true only for the classical field theory, in classical field theory. Because of the subtle effect, so actually instanton effects about which Andreas talked in the lecture. So here we showed explicitly why at the classical level axion is shift symmetric. So now how this symmetry is affected at the quantum level. So actually, yes, at the quantum level, so what we have to take into account that there can be contributions even from the surface terms at infinity. So here, although d mu k mu is a total derivative here, so GG dual is total derivative here, but if we now calculate the integral over d4x, we would assume that the total derivative, so if we just okay, if this integral d mu k mu d4x equals integral d sigma mu so over the sphere at infinity of k mu, so and then we normally say that all the fields vanish at infinity, and that's why this integral is equals to 0. However, it's not true here. So why it is the case? Because actually here in the expression for k mu, we have this extra bizarre part, which is a nu, a lambda, a rho. And this part does not have to vanish at infinity. So this part, yes, because it contains G. But this part, not, because a nu is something not really physical. So, I mean, it's not something which, so it's something not gauge invariant, which can change when you, yeah, okay. If you choose a given gauge. So, and actually it turns out that that this integral of, okay, let me write, d sigma mu epsilon mu nu lambda rho. So this integral in the end is not 0. So even although it is taken on the infinite at infinity, so a nu, a lambda, a rho. So it's not 0 because okay. And here also it is clear that what will contribute to this term is only pure gauge, right? And since a nu, so the gauge transformations of a nu are just omega a nu omega minus 1 plus omega d nu omega minus 1. So only the pure gauge part will contribute. And here we actually have the integral d sigma mu epsilon mu nu lambda rho omega d nu omega d nu omega minus 1 times omega d lambda omega minus 1 times omega d rho omega minus 1. Okay, and where omega is SU3 matrix. So this integral in mathematics, so it's known to be actually topological invariant. So because if you now consider small small changes of omega, so actually one can show easily, just because d nu of omega minus 1 equals 0. So one can show that if we make small changes to omega, this integral will stay the same. So actually, whenever we do some small gauge transformations here, we do not get any different result. And in fact, this yeah, so in fact, this integral parameterizes how we put parameterizes this mapping of a nu at infinity. So a nu at infinity into omega d nu omega minus 1. So omega is SU3 matrix. So and infinity surface is S3 sphere. So actually we just map S3 into SU3 group, but so here actually even so SU3 has SU2 as subgroup, so it's easier even to consider SU2. And here actually SU2 is also isomorphic to this S3, to the 3 sphere, and that's why we just map one sphere on another sphere, and this this mapping calculates the number of times we like wrap one of the spheres over the other one. So it is actually just like if we map a circle into another circle, right? So we can so suppose we have like some kind of circle, and we want to put a rope on it, which is also like a loop. So we want to put a rope on it. So then this integral would calculate. So the analog for the U1 group will just calculate how many ropes how many times this rope wraps around the circle. So yeah, and in the end, what is important to get from all this topological reasoning is that it is actually GG dual term is topological, and actually time when it is multiplied by some coefficient, it just gives us an integer. So that's all what we wanted to say. The exact form, which will give us an integer, is actually 1/16 pi squared. Integral g mu a g mu a dual d for x. So this equals to some number n, and and that's why actually we now see that on the quantum level, now if we want to, so we see that first actually this GG dual is not at the quantum level, this derivative is significant. So the axion actually loses its shift invariance, right? But because of these surface terms. But then if we now want to see what symmetry actually remains even at the quantum level, so we can, so again, okay, for axion we have here A divided by FA, so times this, yeah. So now we want to see 2 factor of 2. Okay. So now we want to see and GS squared. Okay. So now it's not 10. Okay. Messed it up. Okay. So here actually now we want to see what symmetry remains, and actually the symmetry which remains is A shifted by 2 pi n. Why is it so? Because in the path integral, this action enters as e to the is. So actually this s is then e to the, so this s is just an integer which I wrote times the a divided by fa, and that's why yeah, if we add integer multiple of 2 pi's and times fa, of course, sorry, so times fa, if we add this multiple to the axion field, the path integral will stay the same. So actually this is a true symmetry of the axion field, and not just any shift symmetry. And this is also tells us that this GG dual term and instantonic processes which are associated to this surface term, they are actually they also like we can already infer from here that they should provide some kind of potential for the axion. So in the end, this potential, because of this symmetry, and also because we know that axion equals to 0. So here, I mean, if you write this term as a GG dual, then a equals to 0 is the minimum of the potential. So actually, okay, the potential will be like this, periodic, So, and here is this discrete shift symmetry. So because of the potential induced by instantons we have on the discrete shift symmetry. Yeah, so this leads also to important applications of course, like if you have this different, so now you have like the, Zn symmetry here for the potential, and axion can land in any minimum here. For example, during the hot Big Bang, when this instanton processes start to be important, then axion in different patches of the universe, which are not causally connected, the axion will fall in different of this minima. So when the temperature is starts to be not so hot that all this that axion can just travel from one to another, then and this potential starts to be significant, then in different patches of the universe we are left with different axion field values actually, which can be different by this numbers here. And this also means that if we have two such patches, in between them there will be some like transition from one value to the other, and this transition will have some energy because the gradient of the axion field will be not zero. And actually this transitions are called topological defects, and they are the domain walls which form when the universe cools down, so in many axion models. So yeah. Okay. So okay, I think this is the end of the first question which we had. Then okay, had some other ones. Rewrite the Lagrangian. So this Lagrangian in terms of the color electric, color magnetic fields. So okay, it is also just algebra. So in the end, because the time is over, I think we can just okay, let me give the answer. Ga mu nu equals actually just minus 4 Ea Ba. So where E and Ba are the color electric, color magnetic fields. So in the end, the coupling to axions can be rewritten as a coupling of A gs square divided by 8 pi square Fa Ea Ba. And what's interesting here, so from this we can easily answer all the other questions. So first, so here, okay, they asked us whether this term violates some discrete symmetries, right? So now it can be easily inferred. So here we have a color analog of the magnetic field and the electric field, and we know very well how electric and magnetic fields transform, right? So okay, let us make a small table. CPT, electric, magnetic field. So under C, so the charge conjugation will change both electric and magnetic fields because change the sign because they're created by charges, and if you switch the charge, the sign of the charge, you also switch the sign of the field. Then under parity, so the electric field will change because, so if you look at the mirror at the electric field, it changes its direction. If you look in the mirror at the magnetic field, it does not, because the magnetic field is actually, right, it's created by a current. So and the direction of the current, like for example clockwise, it does not change if you have if you reflect it in the mirror, so you will still have magnetic field. here. And then the time inversion does not change the electric field. And for the magnetic field, it actually changes the direction of the current because you inverse the, and then you will get minus. So then you see from this table that actually this term violates, so this violates P, T, and CP, right? So of course CPT is always conserved in the QFT, so you see that everything is consistent here. Okay, next question is, explain why the GG dual expression is Lagrangian, okay, gives rise to the electric dipole moments of nucleons. So this also can be answered quite easily from this expression. So from here we see that, so if, okay, now, so if Lagrangian contains a term like this, then it means that actually any color magnetic field will be, so any color magnetic field will be accompanied by a color electric field. So the color magnetic field can create a color electric field which is in the same direction, right? So this is, if we look at this as a coupling, we can also put it just in the equations of motion and see this. So in the end, so now if we have magnetic moments, so we know that like neutron and proton have spins 1/2, and they have a magnetic moment. So now we will have also electric dipole moment, so color electric dipole moment, but also because you have here also the same E dot B for electromagnetism, you will have also magnetic, okay, so you will also have the magnetic dipole moment, electric dipole moment for electromagnetism. Yes, because yeah, as Pablo explained, any axion which couples to gluons, so we'll have some contribution from the mixing of axion with the neutron mesons to axion coupling to photons. So actually, or so this term will. Okay, so now. And then if we put axion field here, then of course axion governs this coupling, and that's why axion governs couples to the EDMs of nucleons. Okay, and yeah, the last question. So why non-zero EDMs of nucleons violate invariance? So this is also quite easy to answer now. So we can here put so. The spin of a particle, or so, which is one of the kinds of angular momentum, right? So here, for the spin, we will have this and this. So spin is also like an angular momentum with an axial vector. So it will have such transformations, and yes, and so. Okay. And in the end, what we get is that, so from here we also see that any dipole moment, electric dipole moment, will be proportional to the spin, right? So now if we write just Lagrangian for the dipole moment, so we will have the term which is minus d times the electric field. And then we see, looking at the transformation properties of the electric field, looking at the transformation properties of spin, we see that this term, so contrary to the term which will be mu magnetic moment times b, right? So because these two have similar properties under the transformation, and these two not. So that's why this term, it will violate P. So we see that here we have different properties, and T. So yeah, so P, T, and so also CP violation. Okay, so okay, this brings me to the end, and I don't know. So I think I should stop because it's now 12 o'clock. So what do you think? Or I have some time still, because I can briefly also discuss the next exercise.
Maybe it's better if we can if we ask if there are any questions about your exercises.
Yes, okay. So
if there are questions, feel to ask now.
Okay, are there any questions? So actually we solved completely the exercise 1. Skipped some algebra for this derivation, but it's actually straightforward. Okay. So then
any questions?
There are no questions. Finish.
Hello, can you hear me?
Hello, yes.
Yes, sir.
I have a question about this wrapping S3.
Please speak louder.
Can you hear me better now?
Yes, now better.
So I have a question about this wrapping.
Okay.
There is a S3 mapping on the SU2, but QCD is SU3. So the same kind of index could be defined also for other theories like SUN.
Yes, for any SUN, yes, but yes, for any SUN there will be this mapping, and actually, so the significant part of so the significant part of the group which contributes to this is SU2 subgroup. So for any SUN you have SU2 subgroup which will which will be the 3-sphere, and that's why this mapping will be characterized by some integer number.
Okay, thanks.
Okay, are there any other questions?
Okay. There's still time for 1 or 2 questions if you wish.
Yeah,
just unmute yourself.
Yeah, I can say just that then the second exercise, it's also very important also for experiments which are now ongoing looking for Axions. So I think we will briefly discuss it tomorrow. And you can while look at it and try to maybe solve yourself, and, so that I'm not just giving a lecture, but also maybe so.
Okay, maybe tomorrow we discuss again this exercise. So I think we can stop here, and thank again Anton and also Pablo for giving us these exercises. And now we go for lunch, and we meet again at 2 o'clock.